Hello everyone, welcome back to our channel Farm Assist. Today we are diving deep into Volhard's method, a technique used to determine the concentration of chloride ions in a solution. This method involves back titration with potassium thiocyanate, and we'll talk through each step of the process, including the problems encountered and the solutions to overcome them. The primary object of Volhard's method is to accurately measure the amount of chloride ions present in the solution. This is achieved through a meticulous back titration involving key reagents, namely silver nitrate and potassium thiocyanate. To kick things off, an excess volume of a silver nitrate solution is added to the solution containing chloride ions. This is a crucial initial step as it leads to the formation of silver chloride precipitate. This precipitation occurs through the reaction between silver ions and chloride ions, resulting in the formation of silver chloride solid. Okay, the chemical equation representing this process is like this. Okay, by adding an excess volume of silver nitrate, we ensure that all chloride ions in the solution react with silver nitrate. This prepares the stage for the subsequent back titration with potassium thiocyanate. The formation of silver chloride is crucial in this method, as it provides a solid indicator for the presence of chloride ions and allows us to move forward with the titration process. Okay, so as we progress through the steps of Volhard's method, we'll delve deeper into the intricate details of titration process and the calculations involved. Okay, now let's dive into the chemistry behind Volhard's method by examining the key chemical equations involved in the process. The first equation represents the initial reaction, where silver ions from the silver nitrate solution react with chloride ions in the sample solution. This results in the formation of silver chloride as a precipitate. In the next reaction, we introduce potassium thiocyanate into the solution. Silver ions react with thiocyanate ions, leading to the formation of silver thiocyanate as a precipitate. This reaction is essential during the titration process. Now let's focus on the role of ferric ions in the presence of thiocyanate ions. The third equation shows the formation of a complex ions, which serves as the indicator for the endpoint of the titration. These chemical equations are fundamental to the Volhard's method, representing the key reactions that drive the formation of precipitates and complexes essential for accurate chloride ion determination. As we move forward, these reactions will play a central role in understanding how Volhard's method allows us to precisely quantify chloride ions in a solution. Before that, let's cover the titration process. Now that we have initiated the precipitation of silver chloride by adding an excess volume of silver nitrate, let's delve into the subsequent steps of the titration process. The first step is silver thiocyanate precipitation. Okay, after the formation of the silver chloride precipitate, the solution is titrated with the potassium thiocyanate solution. The unreacted or excess silver ions in the sodium now react with thiocyanate ions, leading to the formation of a silver thiocyanate precipitate. This precipitate has a distinctive pale yellow color, serving as a visual indicator of the ongoing chemical reactions. As you can see from the equation, silver ions are reacting with thiocyanate ions to produce the silver thiocyanate precipitate. Second step is indicator role of ferric ion. To monitor the progress of the reaction, ferric ions are introduced as an indicator. The silver ions that remain unreacted after the initial precipitation will now react with thiocyanate ions. However, when the reaction is nearing completion, the excess thiocyanate ions react with ferric ions, forming a dark red complex. This red complex, okay, dark red complex, serves as the endpoint indicator for the titration. The subtle color change from the pale yellow of silver thiocyanate to the dark red complex signifies the completion of the reaction and allows for precise determination. The third step is the calculation of chloride ion determination. Okay. The calculation of determining chloride ions involves subtracting the moles of silver ions that reacted with thiocyanate from the total moles of silver nitrate initially added to the solution. Okay, this step is crucial in obtaining accurate results and quantifying the concentration of chloride ions in the solution. It's this meticulous calculation that adds a quantitative dimension to the qualitative observations made during the titration. In summary, the titration process in Volhard's method is a carefully orchestrated series of reactions that culminate in the formation of a distinct endpoint, allowing us to accurately determine the concentration of chloride ions in the solution. Now let's understand one of the critical factor of pH considerations, okay, in Volhard's method. The pH level of solution after sample preparation plays a pivotal role in the success of this titration technique. Volhard's method is specifically designed to be effective when the solution's pH is acidic. Okay, why is acidic pH crucial? But why? Well, in acidic environment, the reaction conditions favor the formation of the silver chloride precipitate during the initial stage of the procedure. This ensures that all chloride ions in the solution react completely with the added silver nitrate. However, if the pH of the solution is neutral or basic, Volhard's method might not be the most suitable choice. In such cases, chemists often opt for alternative methods like Moore's method or gravimetric method. So bottom line is, for Volhard's method to work optimally, we need to maintain an acidic pH environment. This allows for the successful formation, this allows for the successful formation of the silver chloride and silver chloride precipitate during the initial stages of the process, ensuring accurate results in the determination of chloride ion concentration. It's a crucial consideration to keep in mind when applying this analytical technique in the laboratory. Now that we have already come to an end of this topic, before ending this video, I want to add more information, which includes the problems and solutions of Volhard's method. Okay, let's delve into some of the challenges that can arise during the Volhard titration and the ingenious solutions to overcome them. One common issue faced is the adsorption of silver ions into the initial silver chloride, okay, precipitate, leading to a premature endpoint during the back titration. To tackle this, we employ a couple of effective solutions. Firstly, vigorous shaking of the mixture before the back titration helps to desorb the silver ions, preventing their interference with the accuracy of our results. Another approach involves boiling the mixture for a few minutes. During this process, potassium nitrate is introduced to prevent the resorption of silver ions into the silver chloride precipitate. Now let's talk about another challenge. That was the first challenge. The sparingly soluble salts like silver chloride and silver thiocyanate, okay, are in equilibrium with the solution, creating a potential source of error at the endpoint. At the endpoint of the back titration, the excess thiocyanate ions may react not only with the indicator Fe ions, Fe3 plus ions, but also with silver chloride precipitate. This could result in a higher endpoint than the actual value. To counter this, we need to prevent the reaction between thiocyanate and silver chloride. One effective method is to boil the silver chloride precipitate for a few minutes, followed by a filtration to remove the precipitate. The cold filtrate is then used for the back titration. Alternatively, an immiscible liquid such as nitrobenzene can be used to coat the silver chloride particles, protecting them from reacting with thiocyanate. These precautions are essential to ensure the accuracy and reliability of Volhard titration results. Overcoming these challenges is crucial for obtaining precise measurements in the determination of chloride ions. With these solutions in mind, let's move forward, okay, and explore more. Now we are going to discuss another part of Volhard's method, which is it is also called modified Volhard's method. Okay, so what is the difference between both? Okay, the variation between these two addresses specific challenges, particularly in the determination of sodium chloride, okay, or potassium chloride. Let's dive into the modifications that make this method especially useful. As we move to the next step, let's visualize the setup. When silver nitrate reacts with sodium chloride, silver chloride is formed. However, this silver chloride can interfere with the subsequent titration with potassium or ammonium thiocyanate. To counter this interference, a slight modification is introduced, and that's why it is called modified Volhard's method. Understood? The goal is to prevent the interference of silver chloride with the titration process of excess silver nitrate with potassium or ammonium thiocyanate. Before we delve into the modification, let's quickly recall the key reactions involved in the modified Volhard's method. We have the formation of silver chloride and the subsequent titration with thiocyanate. So how do we prevent the interference of silver chloride? There are two main approaches. Okay, firstly, we can add a layer of immiscible liquid such as nitrobenzene or dibutyl phthalate, which forms a protective layer over the silver chloride particles. This physical barrier prevents the interference during titration. Alternatively, another effective method is filtration. By removing the silver chloride precipitate through filtration, we eliminate the interference, allowing for a more accurate titration of excess silver nitrate with potassium or ammonium thiocyanate. It's important to note the modified Volhard's method is particularly useful when dealing with certain chloride salts, such as sodium chloride and potassium chloride. The choice of modification depends on the specific requirements of the analysis. In conclusion, the modified Volhard's method introduces a clever modification to ensure the accuracy of the titration process, especially in the presence of interfering substances like silver chloride. The adaptation enhances the reliability of chloride ion determinations in specific scenarios. Alright folks, we have covered a lot of ground in our exploration of Volhard's method for chloride ion determination. So in conclusion, Volhard's methods stands as a valuable tool in analytical chemistry, providing a robust approach to chloride ion determination. We hope this comprehensive guide has enhanced your understanding of the method. If you found this video helpful, please considering liking, sharing and subscribing for more insightful content. Thank you for joining us in this video, and we look forward to exploring more topics in the next video. Until then, take care.